Some problems in life feel big, like finding matching socks in the laundry, or figuring out what that mystery Tupperware at the back of the fridge used to be before it evolved into a new life form. But in mathematics, problems can get a little bigger than socks and leftovers. Some problems are so big that they laugh at us. They sit there staring down centuries of brilliant minds, and they say, "Nice try, human, but you're not solving me today." Mathematics is full of legends, not just legends as in really cool people, but legends as in whispered tales of impossible riddles, stories of geniuses who locked themselves away with chalkboards and ink-stained fingers, only to come out years later muttering things like, "Nope, still impossible." These are not just stories about numbers, they are stories about obsession, about failure, about persistence, and about the strange, beautiful, ridiculous dance between humans and the mysteries of the universe. From the moment humans started counting sticks and sheep, we discovered that numbers are slippery little creatures. They look simple. 1, 2, 3. Easy. But keep going long enough, and numbers start acting weird. They hide patterns, they break rules, they whisper secrets that you almost hear but never quite catch. And then there are problems. Problems that start as innocent little questions but somehow turn into beasts that chew up mathematicians and spit them out. Think of it this way. Most of math is like solving a jigsaw puzzle. Sometimes you get the corner pieces quickly. Sometimes it takes a while to see the big picture. But then there are puzzles where the box doesn't even have the right picture on it. You spend centuries flipping pieces over, and nothing fits, and eventually you wonder if the puzzle was designed by some mischievous cosmic trickster who just wanted to see you suffer. That, my friends, is the legend of the unsolvable problem. But before we get too deep, let's be honest. Humanity has always loved riddles, not just math riddles, any kind of riddle. The Sphinx in ancient Egypt basically made riddles her full-time job. Answer my riddle or get eaten. That's a pretty solid business model. In fact, if the Sphinx were around today, she would probably have a very successful YouTube channel, maybe even a podcast. Riddle me this with the Sphinx. I'd listen, probably while falling asleep. Why do we love riddles? Because riddles tickle the brain. They sit in that perfect spot between possible and impossible. They annoy us just enough to keep us interested, but not so much that we give up immediately, except in math. Sometimes that line gets crossed. Some riddles in math have been annoying us not for a day or a week, but for hundreds, even thousands of years. And that's what makes them legendary. These are not just puzzles, they are human stories. They are stories of kings and queens who offered rewards for answers, of monks scribbling away in candlelight, of university professors losing their hair over equations, and of eccentric geniuses who walked away from million-dollar prizes just to go live in the woods with a cat. True story, by the way. We'll get to him later. So what does an unsolvable problem actually mean? Well, it doesn't always mean it's truly impossible. Sometimes it just means that no human has managed to solve it yet. It's like a video game boss with infinite health. People keep attacking, trying new strategies, leveling up, but the boss just yawns and says, "Is that all you got?" And mathematicians, bless them, are not exactly known for quitting. They'll keep coming back for centuries. And when they do, the rest of us get some of the best stories in science. Stories about pride and rivalry. Stories about brilliance and madness. Stories that sound like they belong in fantasy novels rather than math textbooks. The legend of the unsolvable problem is not just about math itself. It's about humans facing something bigger than themselves and saying, "We're not scared. Okay, maybe a little scared, but we're going to try anyway." One of the reasons these problems are so legendary is because of what they promise. Solve one and you don't just get bragging rights, you can change the world. Some unsolved math problems are tied to how we send emails, how we keep bank accounts safe, even how we understand the fabric of the universe. Others are just plain weird, little games that seem silly, but behind them might be the keys to understanding chaos, order, and everything in between. So here's the picture. Imagine a hall of fame, a dark hall with marble walls and statues of ancient thinkers. The torches flicker. In the center of the hall stand a handful of problems carved into stone, each one of them with a plaque that says, "Still not solved." Mathematicians wander in, armed with pencils and coffee. They try, they fail, they try again. Generations pass. Some come close, others crash spectacularly, and the problems remain, watching, smiling, laughing. That's where our story begins. Tonight, or today, or whenever you're listening, we're going to wander into that hall together. Don't worry, it's not going to be scary. Think of it like a museum tour, but the exhibits are math mysteries, and your guide, you guessed it, me, will make sure we stop at the gift shop for snacks. Because if we're going to face the most unsolvable problems in history, we might as well have a good laugh along the way. In this journey, you're going to meet some strange characters: a shy German genius who changed math with a single lecture, computer scientists who accidentally stumbled onto the biggest puzzle of the digital age, a simple little game involving multiplying numbers by 3 that has caused entire conferences of mathematicians to scratch their heads, and of course the million-dollar problem that nobody, not even the smartest minds alive, can solve. That one has been sitting there for over a century taunting us. But before we dive into each of these, remember this: the legend of the unsolvable problem is not just about frustration, it's also about beauty. Because the real magic of math is not in having all the answers, it's in the chase, the curiosity, the thrill of being part of something bigger. Solving problems is great, but living with mysteries, exploring them, telling their stories, that's where the real wonder lies. So get comfortable, let your brain relax. This is not going to be a lecture. This is a bedtime story for the mathematically curious. It's a journey into the strange world where numbers turn into legends, and legends turn into lullabies. Some problems have answers, some don't, and some, well, some just laugh at us. And now, let's step into history, to the first time math drove people completely mad. Spoiler alert, it involved triangles, secret cults, and a number so terrifying that the Pythagoreans swore to keep it a secret forever. If you've ever had a math class that made you want to bang your head against the desk, don't worry, you're not alone. This has been happening to people for thousands of years. In fact, the very first recorded math meltdown happened in ancient Greece, and trust me, it was dramatic. Picture the scene. Around 500 BCE, you're hanging out in a secret cult led by a man named Pythagoras. Yes, that Pythagoras, the triangles guy, the a squared plus b squared equals c squared guy. Except, back then, he wasn't just teaching math. He was running what was basically a cross between a school, a philosophy club, and a very exclusive gym membership that also came with a strict diet plan. Seriously, Pythagoras had rules. His followers, called Pythagoreans, weren't allowed to eat beans. Nobody's sure why. Some say it was because beans looked like tiny little souls. Others say it was just because beans made you gassy, and you can't meditate on cosmic harmony while someone is blowing bean-fueled trumpet solos in the corner. Either way, beans were out. But triangles? Triangles were in. Pythagoras believed that numbers were the ultimate key to understanding the universe. He and his followers thought everything could be explained with whole numbers and their ratios. Music, astronomy, geometry. It was all just numbers singing in harmony. To them, math wasn't just arithmetic. It was a religion. And then, disaster. One day, one of Pythagoras' followers, legend has it his name was Hippasus, made a horrifying discovery. He was working with the diagonal of a square. Simple enough, right? Take a square, draw a line from one corner to the opposite corner. That's the diagonal. Easy. Now measure it. If the side of the square is 1 unit, then the diagonal should be something you can write down as a nice, neat fraction. At least that's what everyone believed. But no. Hippasus found that the diagonal wasn't a fraction at all. It was something monstrous. Something that could not be expressed as a ratio of whole numbers. It was what we now call the square root of 2. This, my friends, was the birth of irrational numbers. And the Pythagoreans absolutely hated it. They believed the universe was built on harmony and rationality. Everything was supposed to fit neatly into ratios. But here was this diagonal rudely screaming, "Sorry folks, I refuse to be a fraction, deal with it." The story goes that the Pythagoreans were so horrified by Hippasus' discovery that they either exiled him or, depending on which version of the tale you prefer, drowned him at sea. Imagine that. You discover a new number, and your reward is being tossed into the Mediterranean. That's how seriously they took it. And you can almost sympathize with them. For people who believed that numbers were the divine building blocks of reality, discovering irrational numbers was like discovering your God has a secret gambling problem. It shattered their worldview. If numbers couldn't always be neat and rational, then what else was out there lurking in the shadows of mathematics? This was math's first big identity crisis, and it wouldn't be the last. Think about it. Today we just shrug and say, oh yeah, the square root of 2 is irrational, no big deal. But back then, this was like a horror movie plot twist. People believed the universe was built on rational numbers, and suddenly, boom, here comes this number that breaks all the rules. It was terrifying. But also, let's be honest, kind of hilarious. I mean, imagine a secret cult of mathematicians running around in panic because one guy discovered a diagonal. I picture Pythagoras himself dramatically dropping a triangle on the floor and gasping, "We have angered the gods." Meanwhile, Hippasus is just standing there like, "Guys, calm down, it's just a number." Of course, once the initial shock wore off, irrational numbers turned out to be incredibly important. They show up everywhere in circles, in triangles, in pretty much any shape you draw. Without them, geometry would fall apart. But back then, it was a scandal. A scandal that showed for the first time that math wasn't always neat and tidy. Sometimes math was messy. Sometimes it drove people mad. And irrational numbers weren't the only problem haunting the Greeks. Oh no, they also had paradoxes. Enter Zeno of Elea, a philosopher who clearly had way too much free time. Zeno invented a bunch of paradoxes that made people question whether motion, space and time even made sense. His most famous one is Achilles and the tortoise. Here's how it goes. Imagine Achilles, the greatest runner in Greek mythology, racing a slow little tortoise. To be nice, Achilles gives the tortoise a head start. Now, by the time Achilles reaches the point where the tortoise started, the tortoise has moved a little bit further. When Achilles reaches that new point, the tortoise has moved again, and so on forever. According to Zeno, this means Achilles can never catch the tortoise because the tortoise will always be just a tiny bit ahead. Now, obviously, in real life, Achilles would sprint past the tortoise, wave goodbye, and be home in time for dinner. But Zeno's paradox forced people to think about infinity, about dividing space and time into smaller and smaller pieces. It was like the universe itself was playing tricks on human logic. So between irrational numbers and paradoxes, math in ancient Greece was basically one long existential crisis. On the one hand, numbers gave order and harmony to the cosmos. On the other, they revealed terrifying truths that didn't fit into neat boxes. It's no wonder the Greeks were always arguing in the marketplace. Half of them were probably still trying to figure out if Achilles ever passed that poor tortoise. Looking back, it's easy to laugh. But here's the important part. These crises pushed mathematics forward. The discovery of irrational numbers forced people to expand their definition of what numbers could be. Zeno's paradoxes pushed philosophers to think deeply about infinity and limits, concepts that would later become the foundation of calculus. The madness wasn't a dead end, it was a doorway. And that's the pattern you'll see again and again in the story of unsolvable problems. First, shock, then panic, then obsession, and finally, progress. The problems that drive us mad are the very ones that force us to grow. So the next time you feel frustrated with a math problem, just remember, you're part of a very long tradition. People have been losing their minds over numbers since the time of Pythagoras. And if Hippasus could survive inventing irrational numbers, well, okay, maybe he didn't survive, but if he could at least discover them, then you can definitely survive your homework. Math is a story, and every great story needs drama. The Greeks gave us plenty of it, and they left behind a legacy. The idea that behind every simple question might lurk a terrifying, irrational, impossible truth. Which brings us neatly to the next chapter in our tale, when mathematics got even messier. Because if irrational numbers made people panic, just wait until algebra hit its rebellious teenage years. Math has always been a little dramatic. First, the Greeks had their existential crisis over irrational numbers. Then they had paradoxes about turtles outrunning superheroes. But if you thought math was done making people sweat, oh no. Next came algebra. And algebra went through what I can only describe as its messy teenage years. Let's set the scene. For centuries, math was mostly geometry. Shapes, triangles, circles, you could draw it in the sand and look very wise. But algebra was like math suddenly deciding to go goth. Instead of drawing, mathematicians started writing little symbols and letters everywhere. It looked mysterious, it sounded mysterious, and half the population had no idea what was going on, which, to be fair, is still how algebra feels to most high school students today. Algebra was born in places like the Middle East and India. The word itself comes from the Arabic al-jabab, which means reunion of broken parts. Very poetic. Basically, algebra was invented to solve equations. You had unknown numbers, and you wanted to figure them out. If you could balance the equation, you won. It was like a puzzle, but with more x's and y's. At first, it was pretty straightforward. Quadratic equations? Solved. Cubic equations? Tricky, but solved. Quartic equations? Those with a fourth power? Also solved. Thanks to some Italian mathematicians who were so competitive about it that they treated math like a gladiator sport. Seriously, in the 1500s, solving equations wasn't just homework, it was a public spectacle. Mathematicians would challenge each other in duels. They'd exchange lists of problems, then stand in front of crowds to see who could solve them faster. Imagine math UFC, but with quills and parchment. One of the stars of this scene was a guy named Niccolò Tartaglia, whose name literally means the stammerer. He had a rough life. He was attacked as a child and left with a speech impediment, but he was brilliant. He figured out a method for solving certain cubic equations, but here's the thing, he kept it secret, because in Renaissance Italy, math solutions were like nuclear codes. Whoever had them could win competitions, get rich and earn fame. Enter Girolamo Cardano, another mathematician, doctor, gambler, and all-around eccentric. Cardano sweet-talked Tartaglia into revealing his method, promising he would never publish it, and then of course he published it. Classic betrayal. Cardano even added a few improvements of his own, and suddenly he was the rock star of algebra. Tartaglia was furious, but history tends to remember Cardano more. So the lesson is, don't trust mathematicians with your secrets. But here's where it gets really interesting. After all that drama, mathematicians had conquered equations up to the fourth degree. They thought, great, we're on a roll. Next stop, quintic equations. Fifth power, easy. But quintic equations were like the boss level that nobody could beat. People tried everything. They bent the rules, invented tricks, sacrificed goats. Okay, maybe not goats, but you get the idea. No matter what they did, they couldn't find a neat formula like the ones for quadratics, cubics, and quartics. For centuries, the quintic mocked them. It was math's way of saying, sorry kid, game over. And then came the bombshell. In the early 1800s, two young mathematicians, Évariste Galois and Niels Henrik Abel, proved that there is no general solution to quintic equations using just algebraic formulas. That's right, not we don't know the solution yet, but the solution doesn't exist. This was a shocking moment in math history. Imagine training for a marathon your whole life, and then someone tells you the finish line doesn't exist. You can run forever, but you'll never get there. That's how mathematicians felt. For centuries they believed that every equation had a neat little solution, and then suddenly, nope. Let's talk about Abel for a moment. Abel was Norwegian, poor and brilliant. He published his proof that the quintic couldn't be solved, but hardly anyone paid attention at first. He struggled to find work, lived in poverty, and tragically died at just 26 from tuberculosis. Only later did people realize how groundbreaking his work was. Today, the Abel Prize is basically the Nobel Prize of Mathematics, named in his honor, a little late, but at least he got recognition eventually. Then there was Galois. Oh boy. If Abel's story was tragic, Galois' was downright operatic. He was a fiery French teenager, politically radical, and also a mathematical genius. He came up with a whole new branch of mathematics, what we now call group theory. While still in his teens, his work explained why some equations could be solved and others couldn't. But here's the twist. Galois died in a duel at the age of 20. And it wasn't even a duel about math. Rumour has it, it was about love. On the night before his duel, knowing he would probably die, Galois stayed up all night writing down his mathematical ideas in a frantic letter. The next day he was shot, and he died a day later. His notes became some of the most important mathematical work of the century. So yes, algebra literally killed people. Forget boring classroom algebra. The history of algebra involves betrayal, duels, heartbreak, and genius teenagers scribbling formulas before getting shot. It's basically a soap opera with extra variables. But the takeaway is huge. For the first time, mathematicians had to face the idea that some problems really were unsolvable. Not just unsolved. The quintic equation was proof that math had limits. That was terrifying, but also strangely freeing, because once you accept that some doors are locked, you stop wasting time trying to kick them down, and you start exploring new paths instead. That's exactly what happened. Galloway's ideas laid the foundation for modern algebra, cryptography, and even physics. From the ashes of Unsolvable, entire new worlds of mathematics were born. Sometimes failure isn't the end, it's the beginning of something better. And that's what makes this chapter in math history so fascinating. It wasn't just about equations, it was about human stubbornness. For centuries, people refused to believe something could be unsolvable. They kept trying, kept dueling, kept betraying each other, until finally 2 young men showed the world the truth. And in doing so, they changed the course of mathematics forever. So the birth of Unsolvable wasn't just about equations. It was about humanity realizing for the first time that the universe might not hand over all its secrets neatly wrapped in formulas. Some mysteries might always stay mysteries. And that's a scary thought. But it's also what makes the story of mathematics so beautiful. The chase is just as important as the answer. Sometimes, maybe even more. Now, having survived irrational numbers and quintic heartbreak, our story moves on to an even stranger battlefield, a place where math and philosophy collide, where questions about infinity and logic spark debates that last centuries. So grab a comfy chair, because next we're heading straight into Plato's Academy, where mathematics became not just numbers, but an all-out war of ideas. If math were just about counting sheep and balancing equations, it might have stayed a quiet little hobby, like knitting or collecting spoons. But somewhere along the way, math met philosophy. And when those two got together, things got loud. Picture ancient Athens. The air is full of dust, arguments, and olive oil. In the middle of it all stands Plato's Academy. This wasn't just a school, it was the world's first university, a place where people came to sit under trees and argue for hours about things like justice, beauty, and whether numbers exist inside our heads or floating somewhere out in the cosmic soup. Plato himself was obsessed with math. Over the door of his academy was supposedly written, "Let no one ignorant of geometry enter here." Imagine putting that over the door of a modern university. Welcome to Harvard. No geometry, no entry. Half the freshmen would be out on the street before orientation. For Plato, math wasn't just useful, it was spiritual. He thought numbers and geometric forms were more real than the messy physical world. In his view, the things we touch and see, tables, chairs, cats, were just shadows. The real truth, the eternal truth, was in the world of ideas. And math, with its clean, perfect shapes, was our ticket into that higher realm. It's a romantic thought, right? That when you doodle a triangle in your notebook, you're not just drawing lines, you're glimpsing into the eternal. But here's the funny part. While philosophers were dreaming about perfect forms, mathematicians were down in the mud, actually trying to solve stuff. And sometimes the two groups didn't get along. Take Aristotle, Plato's star student. Aristotle was more practical. He looked at Plato's talk about eternal forms and said, "That's cute, but how about we study the real world instead?" For Aristotle, math was important, but it wasn't floating in some mystical realm. It was a tool for understanding nature. This split, Plato's mystical math versus Aristotle's practical math, set the stage for 2,500 years of debates. And then there was the small matter of infinity. Infinity is one of those concepts that makes philosophers and mathematicians twitch. On the one hand, infinity is obvious. Numbers go on forever. You can always add one more. Simple. On the other hand, infinity is slippery. How do you actually work with something that never ends? The Greeks argued about this endlessly. Some thought infinity was real, others thought it was dangerous. Zeno, remember him with his turtle. He basically weaponized infinity to annoy people. If you can divide space and time infinitely, does motion even make sense? Does Achilles ever pass the tortoise? Philosophers would sit around all night, drinking wine, arguing about this. Meanwhile, regular citizens just wanted to know when the olives would be harvested. The fear of infinity ran deep. To some, infinity was like staring into the abyss, a place where logic collapses and reason breaks down. Even Aristotle tried to make peace with it by inventing two categories, potential infinity and actual infinity. Potential infinity was like counting, always adding one more, never ending, but never complete either. Actual infinity was the idea that infinity exists all at once as a finished thing. Aristotle basically said, okay, potential infinity is fine, but actual infinity, no thanks. Fast forward to modern times, and mathematicians eventually embraced actual infinity. Hello Cantor and his infinite hotels. But back in ancient Greece, the very idea was terrifying. They didn't even have a symbol for zero yet, so infinity was way out of their comfort zone. Now here's where things get really interesting. Philosophy didn't just influence how people thought about math. It also influenced who got to do math. The Greeks saw math as a noble pursuit, tied to truth and beauty. But later, in the Middle Ages, philosophy and religion got tangled up with math in ways that sometimes made it dangerous. For centuries, certain mathematical ideas were considered suspicious, even heretical. Infinity, for example, was often treated like forbidden knowledge. But even in ancient times, math and philosophy clashed in strange ways. Plato once told a story about prisoners in a cave, chained up, only able to see shadows on the wall. For him, math was the key to breaking free, to turning around and seeing the fire, the real truth behind the shadows. It's a beautiful metaphor, but let's be honest. If you put actual mathematicians in a cave, they'd probably spend all their time calculating the angles of the shadows instead of escaping. The marriage of math and philosophy also gave us some hilarious characters. Take the Stoics. They loved logic, and they treated paradoxes like their favourite party trick. One Stoic thought experiment went like this. If you remove 1 grain of sand from a heap, is it still a heap? What about 2 grains, or 3? At what point does it stop being a heap? This is called the Saurorthorts paradox, and it sounds ridiculous, but it actually reveals how slippery language and definitions can be. And yes, this was considered serious intellectual work. Meanwhile, some poor farmer was just trying to sweep up his wheat. This was the environment in which math started to grow, not as a dry mechanical subject, but as a playground for philosophy, a way of thinking about reality itself. Numbers weren't just tools, they were weapons in debates about truth, existence, and the structure of the universe. And of course, the debates didn't stop. They evolved. Later, in medieval times, philosophers argued about whether math was discovered or invented. Is math out there waiting for us, like buried treasure? Or do we make it up as we go along like a board game with self-invented rules? Even today, mathematicians still argue about this. You'd think after a few thousand years they'd have settled it, but no. Mathematicians love nothing more than arguing about questions that can't be answered. So why does all this matter? Because the fusion of math and philosophy set the stage for everything that followed. Without Plato's obsession with perfect forms, without Aristotle's practical approach, without all those paradoxes and debates about infinity, we wouldn't have the foundation that later mathematicians stood on. The crises of philosophy shaped the crises of math. And honestly, it makes sense. Math is not just about numbers, it's about ideas, about the gap between what we can calculate and what we can imagine, about the tension between the neat little symbols we write on paper and the messy, infinite reality they're supposed to describe. So the next time you see someone staring into space, lost in thought, don't assume they're daydreaming. They might be wrestling with infinity, or they might just be wondering how many beans Pythagoras would allow them to eat. Either way, they're part of a tradition that goes back to Plato's Academy. And that tradition brings us to the next great chapter of our story, a quiet, shy mathematician who gave one lecture that changed everything. His name was Bernhard Riemann, and he introduced a problem that has haunted humanity for over 160 years. A problem that still sits unsolved today, guarding $1 million prize, and possibly the future of the internet itself. Some mathematicians love the spotlight. They write giant books, give dramatic speeches, and make sure their names are carved into the history of math with extra large letters. And then there's Bernhard Riemann, a man so quiet, so shy, and so reserved that if you bumped into him at a party, you'd probably never realize you were standing next to one of the greatest mathematical minds of all time. Riemann was born in 1826 in a tiny village in Germany. His father was a poor Lutheran pastor and the family struggled to make ends meet. Bernhard was painfully shy as a child. He was the kind of kid who blushed when someone said hello and hid behind books when things got overwhelming. Which, to be fair, is exactly the sort of kid who usually grows up to do something earth-shattering in mathematics. From an early age, he showed incredible ability with numbers, but not in the flashy way like solving 300-digit multiplication problems in his head. No, Riemann's talent was more subtle. He had this ability to see deep structures, hidden connections, like he had X-ray vision for mathematics. The problem was he was so nervous and soft-spoken that nobody noticed at first. There's a story that when Riemann was in school, his teacher lent him a copy of a math book by Legendre. Riemann devoured the entire thing in less than a week. Not skimmed, devoured. He understood it so completely that the teacher was stunned. This was not normal behavior for a teenager. Most of us spent our teenage years worrying about zits and whether someone liked our haircut. Riemann was inhaling advanced math textbooks like they were beach novels. Later, he went off to university. At first, he actually studied theology. He thought maybe he'd become a pastor like his dad. But theology lectures weren't exactly his jam. He drifted toward mathematics, and once he landed there, he never looked back. He studied under Carl Friedrich Gauss, the legendary mathematician sometimes called the Prince of Mathematics. Gauss didn't hand out compliments easily, but when he saw Riemann's work, he knew this kid was something special. Now here's the twist. Riemann wasn't just shy. He was painfully shy. Speaking in front of people was his personal nightmare. He was the kind of guy who probably would have fainted if asked to give a wedding toast. But in 1859, he was asked to give a public lecture at the Berlin Academy of Sciences. And in that lecture, this shy, trembling mathematician quietly dropped one of the biggest bombshells in mathematical history. The lecture was titled, in the most boring possible way, on the number of primes less than a given magnitude. Sounds thrilling, right? Almost like on the proper care of houseplants. But behind that dull title was a problem so deep, so mysterious, that it would go on to torment mathematicians for over 160 years. We call it the Riemann Hypothesis. Imagine sitting in the audience that day. You probably showed up half asleep, expecting a dull talk about counting numbers. And then suddenly, this shy man in a black suit, with a voice barely above a whisper, starts outlining an idea that would change the entire field of mathematics. You probably wouldn't even realize at the time what you were hearing. That's how earth-shaking Riemann's lecture turned out to be. But before we get into the hypothesis itself, let's pause and appreciate Riemann as a character. He wasn't the loud, flamboyant type. He wasn't starting math duels in town squares like those Italian algebra guys. He lived quietly, thought deeply, and struggled with poor health his entire life. He never became rich or famous in his lifetime. He was just this quiet genius scribbling away in notebooks trying to peek behind the curtain of the universe. He also had an extraordinary imagination. His work wasn't just number crunching, it was visual, almost artistic. For example, he invented what we now call Riemann surfaces, these strange geometric landscapes where you can untangle complex equations by imagining them as shapes. It was like he was building dream worlds out of math. His creativity set him apart. And yet, Riemann wasn't out there chasing glory. He gave very few lectures in his entire career. The 1859 one, where he introduced his famous hypothesis, was just a short paper barely 9 pages long. 9 pages? That's less than some people's grocery lists. And yet those 9 pages have generated more work, more obsession, more heartbreak than maybe any other piece of mathematics in history. Sadly, Riemann's life was short. He suffered from tuberculosis and eventually moved to Italy, hoping the warmer climate would help his health. He died in 1866 at just 39 years old, which means his entire mathematical career was incredibly brief. But in that short time, he reshaped mathematics in ways still unfolding today. Think about it. A painfully shy poor pastor's son who hated public speaking ends up giving one lecture that changes the future of math, technology, and even the internet. That's the kind of twist you'd expect in a Hollywood movie, not in real life. And that's what makes Riemann mysterious. He didn't write a lot, he didn't talk a lot, and he didn't live very long. We're left with fragments, papers, notes, letters, and one big, terrifying question that he left behind for the rest of us. A question that mathematicians have been trying and failing to answer ever since. The Riemann Hypothesis. So as we leave this chapter, picture Riemann, a quiet man, standing nervously in front of a small audience in Berlin, hands trembling, voice barely audible, sketching out an idea that would echo for centuries. Most of the audience probably left that day thinking, nice talk. They had no idea they had just witnessed the birth of one of the greatest unsolved problems of all time. And that's where our story takes us next, into the hypothesis itself. What did Riemann actually propose? Why is it so important? And why, 160 years later, are the smartest minds alive still banging their heads against it? Let's dive into the strange world of prime numbers and see why Riemann's quiet little lecture turned into math's loudest mystery. Prime numbers are like the celebrities of the math world. Everyone knows about them, everyone talks about them, and nobody really understands what's going on behind the scenes. They're numbers that can only be divided by themselves, and one like 2, 3, 5, 7, 11. They look innocent enough. But behind their simple exterior lies one of the biggest mysteries in all of mathematics. Now, here's the thing about primes. They're the building blocks of numbers. Every whole number is basically made up of primes multiplied together, kind of like atoms are the building blocks of matter. Or if you prefer a more modern comparison, like Lego bricks are the building blocks of every living room carpet injury. Without primes, the whole number system collapses. But here's the weird part. Even though primes are so fundamental, they don't play nice. They show up wherever they want, with no obvious pattern. For example, sometimes you get primes that are close together, like 17 and 19, sitting there like best friends. Other times there are huge gaps between them, like prime deserts where nothing shows up for ages. And no matter how much we stare at them, they refuse to fall into a neat, predictable pattern. Enter Bernhard Riemann, our shy German genius from the last chapter. In 1859, he proposed a daring idea, an idea that could explain the mysterious distribution of prime numbers. His hypothesis, now known as the Riemann Hypothesis, is one of the most famous unsolved problems in math. Some people call it the holy grail of mathematics. Others call it a nightmare. Either way, it's a big deal. So what does it actually say? Well, here's the bedtime-friendly version. Riemann was studying something called the zeta function. Now don't worry, we're not going to dive into scary formulas. Just imagine the zeta function as a sort of magical machine that takes numbers, puts them through a blender, and spits out weird patterns. Riemann realized that if you could understand where this machine outputs 0, where the function collapses, you could also understand how prime numbers are spread out. And here comes the famous hypothesis. Riemann proposed that all the interesting zeros of the zeta function line up neatly on one straight line in the complex number plane. That's it, that's the big mystery. All the zeros marching in perfect formation like tiny mathematical soldiers lined up on what's called the critical line. Now, I know what you're thinking. That doesn't sound too bad. Just prove they all line up right. Easy. Well, mathematicians have been trying for 160 years, and nobody has managed to do it. They've checked billions of zeros with computers, and every single one so far has fallen exactly on the line, like Riemann predicted. But proving that they all do forever, infinitely many of them, that's the monster. Why does this matter so much? Because if Riemann was right, it would unlock the secret code of primes. We'd finally have a clear understanding of how primes are distributed. It would tie together number theory in a way that makes everything click. Imagine solving a jigsaw puzzle and suddenly realizing all the pieces actually do fit together. It would be that moment, but on a cosmic scale. And if he was wrong? Oh boy. If even 1 0 turns out not to be on the line, it would shatter a huge chunk of modern mathematics. Entire proofs and theories would crumble. Cryptography, the stuff that keeps your credit cards safe online, might suddenly become insecure. The internet itself could be in trouble. In other words, this isn't just an abstract math game. The Riemann hypothesis has real-world stakes. Think about that for a second. A quiet little German guy in a short 9-page paper may have accidentally written the fate of the internet. Not bad for someone who barely liked to give lectures. But back to primes for a moment. To give you a sense of why they're so slippery, let me tell you a story. In the 1700s, a mathematician named Adrien Marie Legendre tried to guess a formula for how many primes there are below a given number. He came up with something that worked okay, but not perfectly. Then along came Carl Friedrich Gauss, the prince of mathematics, who also guessed a formula when he was just a teenager. His formula worked much better. This became known as the prime number theorem. But Riemann took things further. His hypothesis gave mathematicians a way to sharpen the prime number theorem, to predict with stunning accuracy where primes would show up. It was like moving from fuzzy binoculars to a high-definition telescope. If proven, it would essentially be the Rosetta Stone of prime numbers. Now, here's the kicker. The Riemann hypothesis is so important that it was chosen as one of the 7 Millennium Prize problems. These are the 7 hardest unsolved math problems in the world, chosen by the Clay Mathematics Institute in the year 2000. Solve any one of them, and you get $1 million prize. That's right, $1 million just for proving a math problem. And so far, only one of the 7 has ever been solved. The Riemann hypothesis is still sitting there, mocking us, daring someone to crack it. But the money isn't even the main attraction. Mathematicians would chase this problem even if the prize was a coupon for half-off pizza. It's about pride, glory, and the irresistible allure of unlocking one of math's deepest secrets. So here we are, billions of zeros checked, all of them lining up like good little soldiers. And yet, no proof. Some of the smartest minds in history have tried and failed. Entire bookshelves are filled with attempts, half-proofs, clever tricks, and dead ends. The Riemann hypothesis remains stubbornly unsolved. And that's why it rules the primes. It's not just a problem. It's the problem, the one that holds the keys to the kingdom, the one that could change how we see numbers forever. And maybe that's why mathematicians are so obsessed with it. Because deep down, it's not really about the zeros or the critical line. It's about the dream of finally taming the wild chaos of the primes. So as you drift off, think about this. Somewhere right now, a mathematician is hunched over a notebook, scribbling furiously, convinced they're one step away from solving the Riemann hypothesis. Maybe they are, maybe they aren't, but until the day someone finally cracks it, the primes will keep laughing, and the legend will keep growing. And in our next chapter, we'll follow the hunt itself, from Gauss to modern computers, from false proofs to spectacular failures. We'll see just how far humanity has gone in its obsession with Riemann's great mystery. If you ever want to see the definition of obsession, don't look at stamp collectors or people who watch every single episode of a soap opera that's been running for 40 years. Look at mathematicians chasing the Riemann hypothesis. This is obsession on another level. From the day Riemann dropped his little 9-page bombshell in 1859, mathematicians have been chasing it like a cat chasing a laser pointer. Except in this case, the laser pointer is infinity, and the cat is slowly losing its mind. Let's start with Carl Friedrich Gauss. Technically, Gauss came before Riemann, but his fingerprints are all over this story. As a teenager, yes, a teenager, Gauss had already figured out patterns in the way prime numbers were distributed. While other teenagers were stressing about acne and crushes, Gauss was calculating the density of primes. His ideas became the foundation for what we now call the prime number theorem. Later, Riemann's hypothesis would provide the missing sharpness, the clean explanation of why Gauss's guess worked so well. After Riemann's 1859 paper, the hunt was on. Mathematicians began trying to prove once and for all that all the non-trivial zeros of the zeta function really do sit on the critical line. And for the next century and a half, the story becomes a saga of failed attempts, bold claims, and occasionally outright mathematical drama. In the early 20th century, G.H. Hardy, one of Britain's most famous mathematicians, made progress. He proved that infinitely many of the zeros do in fact lie on the line. That was huge, but proving that all of them do, that's the Everest that nobody could climb. Around the same time, Hardy's student John Littlewood worked on the hypothesis too. Together, Hardy and Littlewood became a legendary duo in number theory. They even had a list of conjectures about prime numbers that mathematicians are still chewing on today. It's like they left a trail of breadcrumbs leading into the deepest forest of math, and everyone else has been lost in there ever since. Then came the computers. By the mid-20th century, mathematicians realized they could use machines to check the zeros of the zeta function, and check they did. Thousands, then millions, then billions of zeros. Every single one landed neatly on the critical line, just as Riemann predicted. Computers have pushed this verification so far that at this point, if even a single zero wandered off the line, it would be the scandal of the century. But here's the catch. No matter how many zeros you check, you can never be sure about all of them. Infinity is stubborn that way. It's like trying to prove every single grain of sand on Earth is beige by looking at a few million of them. It's impressive, but it's not a proof. The proof has to cover them all, forever. And so the hunt continues. Every now and then, someone claims they've solved it. Headlines pop up. Mathematician claims proof of Riemann hypothesis. People get excited. And then, inevitably, the proof collapses under scrutiny. Mathematicians are very good at tearing apart proofs. It's basically their favourite sport. If your proof has even the tiniest hole, they'll find it, and they'll enjoy finding it. One of the most famous false alarms came in 2004. A mathematician named Louis de Brange, already famous for proving something called the Bieber-Bart conjecture, announced he had a proof of the Riemann hypothesis. The math community collectively raised an eyebrow. If anyone could do it, maybe it was de Brange. But after careful inspection, nope, holes everywhere. Back to square one. And that wasn't the first time. Over the decades, countless proofs have surfaced, only to be debunked. There's even a kind of folklore among mathematicians. If you see an email that starts with "I have proven the Riemann hypothesis," you can safely delete it without reading. It's like the math version of spam. But here's the thing. Every failed attempt isn't really a failure. Each one pushes the field a little further, teaches us a little more, opens up new paths. That's the paradox of chasing an unsolvable problem. Even if you never catch it, the chase itself changes the landscape. And the stakes are high. Remember the Clay Mathematics Institute? In 2000, they announced 7 Millennium Prize problems, each with a $1 million reward. The Riemann hypothesis was on that list. To this day, it sits there, untouched. $1 million just waiting for someone to crack it. That's enough to buy, well, not much real estate these days, but at least a decent supply of coffee to fuel your late-night scribbling sessions. But mathematicians don't chase this for the money. At least not mostly. They chase it for glory, for history, for the sheer thrill of solving one of humanity's deepest riddles. Imagine being the person who finally cracks the Riemann hypothesis. Your name would be etched in textbooks forever. Statues might be built. Math students would curse your name while memorizing your proof, which is the truest form of immortality. So the hunt goes on. Universities, research institutes, lone geniuses in their basements, they're all in the game. Some people try to tackle it with advanced analysis, others with geometry, others with random new ideas that sound completely bonkers. Nobody knows which path, if any, will lead to success. And maybe that's what makes it beautiful. The Riemann hypothesis is like a mountain shrouded in fog. We know it's there, we can see glimpses of its shape, we've climbed parts of it, but the summit remains hidden. Some say we'll reach it one day. Others say maybe it can't be reached at all. Either way, the climb has given us incredible views along the way. So, what have we learnt so far? Billions of zeros have been checked, all on the line. Dozens of proofs have been proposed, all torn apart. The hypothesis stands, untouchable, like some mythic creature that always slips away just as you think you've caught it. And here's the twist. If one day someone finally proves it, part of me thinks mathematicians will be both ecstatic and a little bit sad, because the chase will be over, the mystery will be solved, and sometimes the mystery is the best part. But we're not done with Riemann yet. Next, we're going to explore why this problem matters so much outside the ivory towers of math departments. Because believe it or not, this shy German's hypothesis has real-world consequences. It's not just about numbers on a page. It's about the safety of your bank account, the security of your emails, and maybe even the survival of the internet itself. At first glance, the Riemann hypothesis looks like one of those problems that only matters to people who wear tweed jackets with elbow patches. A problem about zeros and functions and critical lines. The kind of thing that sounds very impressive at dinner parties but doesn't seem to affect your daily life. But here's the secret. The Riemann hypothesis isn't just some dusty puzzle for mathematicians to argue about in chalk-filled classrooms. It matters. A lot. In fact, if it turned out to be false, your whole life would get weird very fast. Let me explain. Remember prime numbers? Those stubborn little indivisible numbers that refuse to play by the rules? Well, primes are the foundation of modern cryptography. Cryptography is just a fancy word for keeping secrets safe. It's the math that locks your online banking, secures your credit card transactions, and makes sure your Netflix password doesn't get stolen by your neighbor who refuses to buy their own account. Here's how it works. The internet uses something called RSA encryption, which relies on prime numbers. The basic idea is simple. Multiplying two primes is easy, but breaking a number back down into its prime factors is hard. Like really hard. If I give you the number 221, you can figure out it's 13 times 17 with a little effort. But if I give you a number with hundreds of digits, good luck. That's essentially impossible with current technology. And that impossibility is what keeps your secrets safe. The difficulty of factoring big numbers is the padlock on the digital world, and the Riemann hypothesis. It's like the instruction manual for how those primes are distributed. If it's true, mathematicians can predict primes with much greater precision. If it's false, then the ground under our cryptographic systems suddenly looks a lot shakier. Now don't panic. Nobody's saying your emails are about to be read by your cat. But the point is, the Riemann hypothesis isn't just academic, it has teeth. It could affect the way we secure everything from military secrets to online shopping carts. And that's not all. The hypothesis shows up in physics too. The distribution of the zeros of the zeta function, those mysterious points on the critical line, seems to match patterns we see in quantum mechanics. Quantum mechanics, if you haven't been keeping score, is the branch of physics that governs atoms, particles, and everything weird about reality. So yes, the same math that helps us understand primes might also help us understand the universe at its smallest scales. This crossover is so uncanny that some physicists have suggested the Riemann hypothesis might actually be connected to the laws of physics. Imagine that. The solution to one of math's deepest riddles could also explain why particles behave the way they do. It's like discovering your grandma's cookie recipe also explains black holes. And if you think that sounds wild, consider this. Some researchers have found connections between the Riemann zeta function and chaos theory. Chaos theory is the study of systems that look random but actually have hidden patterns like weather or traffic or why your hair refuses to cooperate on important days. So by studying the Riemann hypothesis, we're not just learning about primes, we might also be learning about the deep structure of chaos itself. But wait, there's more. Because of its connection to primes, the hypothesis reaches into almost every branch of mathematics. Number theory, analysis, geometry, probability, you name it. The Riemann hypothesis has poked its nose into it. Proving or disproving it would send shockwaves through math like a tectonic shift. Textbooks would have to be rewritten. Professors would have to re-record all their lectures. Students would get brand new headaches. It would be chaos, but also progress. That's why it's one of the Millennium Prize problems. The Clay Mathematics Institute didn't pick 7 random questions out of a hat. They picked the ones that matter, the ones whose solutions would reshape entire fields. The Riemann hypothesis is right up there with problems about quantum field theory, fluid dynamics, and whether P NP. It's math on the edge of civilization. Let's put it this way. If tomorrow morning you wake up, open the news, and see the headline, "Mathematician proves Riemann hypothesis," you may not immediately spit out your coffee. But behind the scenes, mathematicians, computer scientists, and cryptographers would be losing their collective minds. Within hours, teams of engineers would be scrambling to update security systems. Physicists would be checking if their models suddenly made more sense. And somewhere, a few thousand math graduate students would be crying because their entire thesis just became irrelevant. But let's flip it around. What if the Riemann hypothesis is false? What if one rogue zero is hiding out there laughing at us? Well, that would be even more dramatic, because it would mean that centuries of assumptions were wrong. Whole branches of math built on the hypothesis would need to be re-examined. It would be like pulling a card out of a house of cards and watching the whole thing wobble. This is why the Riemann hypothesis matters more than you think. It's not just a puzzle about zeros. It's the linchpin holding together a huge part of our understanding of numbers, patterns, security, and even physics. And maybe that's why people are so obsessed with it. Because deep down, humans love mysteries that matter. A crossword puzzle is fun. A riddle is entertaining. But a mystery that could decide the fate of the internet? That's irresistible. So when you hear about mathematicians hunched over chalkboards at 3 a.m. muttering about zeta functions, remember this. They're not just chasing an abstract dream. They're working on a problem that could ripple into your daily life. Whether you're shopping online, checking your bank account, or streaming a late-night movie. And here's the most ironic part. Riemann himself had no idea his little 9-page paper would become so important. He wasn't thinking about credit cards or Netflix. He was just following his curiosity. He was just wondering about primes, and that's the magic of mathematics. Sometimes the most innocent questions lead to the most world-changing answers. So the next time you see the words Riemann hypothesis, don't roll your eyes and think it's just another math thing. Think of it as the quiet riddle that rules our modern world. a problem that sits silently in the background, holding our digital lives together. And now that we've seen why it matters, let's zoom out again, because the Riemann hypothesis isn't the only great unsolved problem out there. In fact, it's just one of several math riddles that have driven people crazy. Next up, we're diving into a problem so slippery it has computer scientists arguing endlessly: the infamous P versus NP. If the Riemann hypothesis is the mysterious old king of math problems, then P versus NP is its flashy, rebellious teenager. This is the problem that computer scientists whisper about in hallways, that makes grad students cry into their keyboards, and that has kept Silicon Valley billionaires awake at night. So what is this infamous P versus NP thing? Let's ease into it with a story. Imagine you're planning a trip. You've got 10 cities to visit, and you want the shortest possible route that goes through all of them once. This is the famous traveling salesman problem. It sounds simple, right? Just check all the possible routes and pick the shortest. The problem is, the number of possible routes explodes faster than popcorn in a microwave. With 10 cities, it's already millions of options. With 20 cities, it's more possibilities than there are atoms in the universe. Your poor laptop would burst into tears before it even got started. That's where P versus NP comes in. P stands for problems that are solvable in polynomial time, basically problems computers can handle efficiently. NP stands for problems where you can check a solution quickly, but finding the solution might take forever. The million-dollar question is, are P and NP actually the same? In other words, if you can check the answer quickly, does that mean there must also be a quick way to find the answer? If the answer is yes, if P equals NP, it would mean that all those impossible-looking problems, from the traveling salesman to designing new drugs to scheduling airline flights, could suddenly be solved efficiently. It would be like giving humanity a cheat code to the universe. Sounds great, right? Hold on, there's a dark side. Because if P equals NP, then every encryption system we use today would also collapse. Remember how we said your online security depends on factoring big numbers being hard? If P equals NP, that wouldn't be hard anymore. Hackers could crack your bank account faster than you can say password 123. Your credit card, your emails, even the nuclear codes, poof, wide open. So yeah, high stakes. And here's the kicker: nobody knows the answer. For decades, mathematicians and computer scientists have tried to prove whether P equals NP or not. Most people believe the answer is no, that P does not equal NP. In other words, some problems really are hard, and there's no magic shortcut. But proving that belief has been maddeningly difficult. The problem was formally introduced in the 1970s by Stephen Cook and Leonid Levin, and it quickly became the crown jewel of computer science. It's one of the Millennium Prize problems too. Solve it and you get $1 million, and maybe eternal fame, or eternal infamy, depending on what your proof does to the world. The funny part is, we live in a kind of Schrodinger's cat situation with this problem. If P equals NP, then we could solve things like protein folding instantly and maybe cure diseases faster. But also, goodbye privacy. If P doesn't equal NP, then security is safe, but the dream of solving hard problems quickly stays out of reach. Either way, it's dramatic. Now, let me give you a sense of how weird this gets. Imagine Sudoku, a classic NP-type problem. If I hand you a completed Sudoku grid, you can check in seconds whether it's correct. But if I give you an empty grid and say, fill it out, well, that could take you forever. Multiply that difficulty by 1,000, and you get the kinds of problems computer scientists wrestle with daily. Some mathematicians joke that if someone ever proved P equals NP, the news wouldn't actually get out. Governments would suppress it immediately, because the first person to use that proof could take over the internet before anyone else even knew what was happening. It sounds like a sci-fi movie plot, but it's not far from reality. And of course, there have been false alarms. Every few years, someone posts a proof online claiming to have solved P versus NP. The math community rolls its eyes, takes a quick look, and usually finds a glaring flaw. It's become such a running joke that you could almost make a drinking game out of it. New proof of PNP posted to Arxiv, SIP, turns out it doesn't work, SIP. By the end of the evening, you'd be as dizzy as the mathematicians who keep reading those papers. But jokes aside, P versus NP is no laughing matter. It cuts to the heart of what computation even means. What problems can we solve, and what problems are forever beyond reach? It's not just a math puzzle, it's a question about the limits of human knowledge. And here's my favourite part. The problem is simple enough to explain to anyone. You don't need advanced training to get the gist. If checking an answer is easy, is finding the answer also easy? That's it. That's the million-dollar problem. It's like maths version of a riddle you could tell at a bar. The difficulty isn't in understanding the question. The difficulty is in proving the answer. That's the magic of P versus NP. It's like the travelling salesman himself. He's been wandering around for decades, looking for the shortest route home, and every time someone thinks they've found a shortcut, it turns out to be a dead end. Meanwhile, the salesman is still out there, eternally travelling, eternally unsolved. So here we are, a problem that could either save humanity or destroy online banking. A problem so simple to ask but so impossible to answer. A problem that has broken computer science into endless debates and conferences full of very tired researchers. And just like with the Riemann Hypothesis, the hunt for a solution has become as legendary as the problem itself. Whether or not we ever get an answer, P versus NP will keep haunting us, whispering that maybe, just maybe, there's a shortcut out there waiting to be discovered. But before we get too lost in hacker doomsday scenarios, let's move to the next part of the story. Because if P versus NP asks, what if the impossible were easy? Then the next problem is the opposite. It asks, what if the easiest looking problem in the world is actually impossible? Welcome to the strange little bedtime riddle known as the Collatz Conjecture. Let's play a little thought experiment. Imagine you wake up tomorrow, check your phone and see the headline, Mathematician proves PNP. At first you'd probably scroll past it. It looks like one of those headlines you don't click, like scientists discover new type of moss or local man collects 10,000 spoons. Not exactly gripping, but in reality, that one little line would be the end of the internet as we know it. Here's why. Remember how encryption works? The entire system of online security is built on the fact that some problems are easy in one direction and impossible in the other. Multiplying two prime numbers, easy. Breaking a giant number back down into its primes? That's the impossible part. The part that keeps your bank account, your emails, and your embarrassing Spotify playlist safe. But if P equals NP, then suddenly, the impossible isn't impossible anymore. If you can check an answer quickly, you can find it quickly too. Which means factoring giant numbers would become as easy as peeling a banana, and that means every lock on the internet, every password, every secure connection, every HTTPS in your browser would snap open like cheap padlocks at a flea market. Your credit card, gone. Your medical records, public. Your cat's Instagram account, hacked instantly. Governments would panic, banks would scramble, and somewhere in a dark room, a 12-year-old with a laptop would suddenly own half the world's Wi-Fi routers. Now, you might be thinking, okay, but if it works for hackers, doesn't it also work for the good guys? Couldn't we use this magical shortcut to build better security? Sure, eventually, but for a while it would be total chaos, like knocking over a giant Jenga tower before anyone has time to rebuild it. The entire digital world would collapse, and we'd have to redesign everything from scratch. And that's just the scary part. There's also the exciting side, because if P really does equal NP, then suddenly every hard problem with an easy-to-check answer would be solvable in record time. Imagine scientists being able to model protein folding instantly. Right now, designing new drugs or vaccines can take years of trial and error. With PNP, we could potentially discover life-saving treatments in days. Or think about logistics. Airplane routes, shipping networks, traffic systems, right now they're nightmares of complexity. With PNP, you could optimize them perfectly, saving billions of dollars and reducing pollution. Grocery stores wouldn't run out of bananas, delivery trucks wouldn't waste fuel circling neighborhoods, and maybe, just maybe, the cable guy would actually show up on time. In fact, a lot of everyday annoyances could vanish. Your computer could schedule your week perfectly. Your phone could pack your suitcase for maximum efficiency. Even puzzles like Sudoku or crosswords would be trivial. You could solve the New York Times Sunday crossword in milliseconds, which, okay, kind of takes the fun out of it. But still, basically the world would become super efficient. Problems that look impossible now would melt away. Diseases, traffic jams, even some of the biggest mysteries in science could fall like dominoes. Humanity would level up. It would be like going from dial-up internet to fiber optics overnight. But let's not get too dreamy. because remember the dark side. Privacy would be gone, security would be gone, any secret you've ever had would be one computer program away from being revealed. In the wrong hands, PNP wouldn't just be a breakthrough, it would be a weapon. Some people even argue that if anyone ever proved PNP, they should keep it a secret. Don't publish it, don't share it, don't even whisper it. Just lock it away and never let it out, because the first person to exploit it would have absolute power. It's like the ultimate cheat code. Imagine a single person who could break into every bank, every email, every government server on the planet. That's not a mathematician anymore. That's a supervillain. And here's where it gets funny. Even though P versus NP is one of the deepest problems in computer science, the basic question is so simple that you can explain it to a child. If it's easy to check an answer, is it also easy to find the answer? That's it. That's the whole riddle. The consequences, though, are anything but simple. The majority of experts believe PID does not equal NP. In other words, some problems really are hard, and they'll always stay hard. That's why we can sleep at night without worrying that someone is stealing our credit card while we dream. But the possibility that P might equal NP is just unsettling enough to keep people awake at conferences, scribbling proofs on napkins, and hoping for glory. And if it ever is proven, it will be one of the biggest oh no and oh wow moments in human history. Happening at the exact same time, half the world would be panicking, the other half would be celebrating, and everyone would be wondering what comes next. So next time you type your password, take a second to thank the stubbornness of hard problems. Thank the fact that factoring is tough, that optimization isn't easy, and that P and NP are still sitting on opposite sides of the fence, because if someone ever tears that fence down, the world will never look the same again. And speaking of tearing down fences, the debates about P versus NP have been raging for decades. Mathematicians have bet money on it, argued at conferences, and written enough papers to bury a library. Which brings us to our next stop, the endless debates, the false alarms, and the human drama behind the most infamous question in computer science. If you've ever watched two people argue about something they'll never agree on, like which way the toilet paper roll should face, or whether pineapple belongs on pizza, then you already understand the vibe of the P versus NP debates. Except instead of pizza toppings, the stakes here are the future of mathematics, computer science, and possibly civilization itself. The P versus NP problem was formally defined in the 1970s, but the argument started immediately. Some mathematicians were convinced P equals NP, others were convinced it doesn't, and just like any great debate, neither side has proof, which means they've been shouting at each other across lecture halls and conferences for decades. One famous mathematician, Richard Lipton, once compared the question to religion. People just believe. Some believe P equals NP, some believe it doesn't, and both sides cling to their faith with the stubbornness of a toddler refusing to eat broccoli. And let me tell you, the debates can get intense. There are papers, rebuttals, counter-rebuttals, whole conferences dedicated to arguing about this one question. People have even bet money on it. That's right. Serious mathematicians have placed actual wagers on whether P equals NP. It's like Vegas, but instead of betting on horse races or boxing matches, they're betting on the difficulty of Sudoku. One of the most famous bets was organised by Donald Knuth, the legendary computer scientist. He and a few others agreed to pay out depending on how the problem turned out. If P equals NP, one side collects. If it doesn't, the other side does. So far, nobody has collected. The bet is still open, hanging in the air like an unfinished punchline. And then there are the false proofs. Oh boy. Every few months, someone pops up claiming they've solved P versus NP. Sometimes it's a respected mathematician. Sometimes it's a random person on the internet who once solved a Rubik's Cube in under a minute and thinks they're ready for the big leagues. They publish a paper, or a blog post, or an email that starts with "Dear Sir or Madam, I have solved PNP," and the math community groans in unison. Here's the usual cycle. A supposed proof appears, people get curious, experts dig in, and within a few days, someone finds a glaring hole. Maybe the logic doesn't work. Maybe the argument is circular. Maybe the author accidentally assumed the thing they were trying to prove. Whatever the reason, the proof collapses. The cycle repeats. At this point, mathematicians are so used to it that they don't even get excited anymore. It's like the boy who cried wolf. except the wolf is an algorithm that can destroy the internet. There's even a joke in the community. If you think you've solved P versus NP, the first thing to do is wait until the next morning. If you still think you've solved it, put your proof in a drawer for a week. If after a week you still believe it, show it to a friend. If after a month your friend hasn't laughed at you, maybe you should think about publishing. The debates get philosophical too. Some argue that if P equals NP, then the human concept of creativity might not be unique. Think about it. If problems like composing music, writing poetry, or designing a new building could all be reduced to efficient algorithms, then computers could, in theory, do everything humans do. That's either exciting or terrifying, depending on whether you're an optimist or someone who's already worried your toaster is plotting against you. Others argue that P not equaling NP is what makes life interesting. The idea that some problems really are hard, that not everything can be solved with a quick trick, gives the world depth. If everything were easy, maybe life would be boring. Although personally, I'd be willing to test that theory with a world where folding laundry is instantly solvable. And through it all, the debates rage on. Conference after conference, paper after paper, late-night arguments fueled by bad coffee and worse pizza. Mathematicians can't help themselves. It's the ultimate what-if question. What if the world is secretly simple? What if it's irreducibly complex? What if we've been thinking about the whole thing the wrong way? The funniest part is that everyone has an opinion. Even mathematicians who don't work anywhere near computer science have some belief about P versus NP. Ask a random topologist or a geometer what they think, and they'll shrug and say, "Oh, definitely not equal," or "Oh, for sure equal," as if they've just announced their favourite sports team. In other words, P versus NP has become less of a math problem and more of a cultural phenomenon, a campfire story, a riddle everyone loves to argue about, knowing full well they probably won't live to see the answer. And maybe that's the secret to its charm. Humans love unsolvable debates. Coke versus Pepsi, Beatles versus Stones, toilet paper over or under. These things never die because they don't have a definitive answer, at least not one we can agree on. P versus NP lives in that same space. It's the eternal debate of computer science, the one problem guaranteed to start a lively conversation at any math conference. So the arguments continue, and until someone finally proves it one way or the other, they'll keep continuing. Bets will hang in limbo, fake proofs will keep appearing, and conferences will echo with the sound of mathematicians politely roasting each other's logic. But enough about debates. Because while P versus NP keeps computer scientists tossing and turning at night, there's another problem that has a completely different flavour. This one doesn't need supercomputers or complex algorithms. In fact, it's so simple a child can understand it. And yet, it has stumped the greatest mathematicians alive. It's time to meet the Collatz Conjecture, also known as the bedtime riddle that refuses to go to bed. Some math problems are so complicated they require years of training just to understand the question. The Collatz Conjecture is not one of those problems. In fact, it's so simple you can explain it to a kid at bedtime, and yet this tiny, innocent-looking puzzle has driven mathematicians absolutely bonkers. Here's how the game works. Pick any positive number. Doesn't matter which one. Got one in your head? Great. Now follow this rule. If the number is even, divide it by 2. If the number is odd, multiply it by 3 and add 1. Then take the new number and do the same thing again. Even, divide by 2. Odd, multiply by 3 and add 1. Repeat. Keep going. Seems simple, right? But here's the strange part. No matter what number you start with, big, small, prime, composite, whatever, you always seem to end up in the same boring loop. 4, 2, 1, 4, 2, 1, 4, 2, 1, forever and ever. That's it. That's the whole puzzle. It's called the Collatz Conjecture, after Lothar Collatz, the German mathematician who introduced it in 1937, and despite being childishly easy to explain, nobody has ever been able to prove it's true. To make this more fun, let's play a quick round together. Say you start with the number 6. It's even, so divide by 2. That gives 3. 3 is odd, so multiply by 3 and add 1. 10. 10 is even, divide by 2. 5. 5 is odd, multiply by 3 and add 1. 16. 16 is even, divide by 2. 8. Divide by 2 again. 4. Divide by 2 again. 2. Divide by 2 again. 1. And once you hit 1, you're trapped in that little loop. 4, 2, 1, forever. Okay, that was fun. Now try it with 27. Oh boy. Starting with 27 gives you a sequence that takes 111 steps before you finally get down to 1. Along the way, it climbs all the way up to 9,232. Imagine that. You start with a small innocent number like 27, and suddenly you're riding a roller coaster that shoots up into the thousands before spiraling back down. That's why people love this problem. It's chaotic, unpredictable, and yet somehow always ends the same way. Every number anyone has ever tested eventually falls into that 4 to 1 loop. Computers have checked trillions of starting numbers, and none of them have escaped. And yet, no one can prove it's always true for all numbers. That's the maddening part. It looks true. It feels true. Every test says it's true, but mathematics doesn't work on feelings. You don't get points for "I'm pretty sure." You need proof, and the proof, if it exists, has been hiding for nearly a century. The Collatz Conjecture is the ultimate looks easy but isn't riddle. It's like being challenged to fold a fitted sheet. You think, how hard could it be? And then 15 minutes later you're tangled in cotton, questioning all your life choices. And mathematicians are not immune. Paul Erdos, one of the most prolific mathematicians of the 20th century, famously said, "Mathematics is not yet ready for such problems." That's coming from a guy who wrote over 1,500 papers in his lifetime. He called the Collatz Conjecture utterly hopeless, which is mathematician speak for, "Yeah, I'm not touching that one." But of course, hopeless just makes people more obsessed. The Collatz Conjecture has inspired endless papers, YouTube videos, computer programs, and late-night scribbles on napkins. Everyone thinks maybe, just maybe, they'll spot the hidden trick, and every time the conjecture laughs in their face. What makes it so intriguing is how it combines order and chaos. On the one hand, the rules are dead simple. Divide by 2 if even, triple and add 1 if odd. Nothing fancy. On the other hand, the sequences you get are wild. Some numbers shoot up, some numbers fall fast, some meander like they're sightseeing along the way. It feels random, but it's not. It feels predictable, but it's not. It lives in this weird twilight zone where chaos and order hold hands and dance. And here's the kicker. If the Collatz Conjecture were ever disproven, it would mean there's some number out there, hiding in the infinite wilderness, that never falls into the 4-2-1 loop. Maybe it escapes upward forever. Maybe it cycles in some bizarre new loop we've never seen. Nobody knows. And the idea that such a number might exist is both terrifying and thrilling. So far, no escapees. Every tested number has been captured by the loop. But remember, infinity. We can't check them all. Somewhere out there, past the reach of computers, could lurk a rebel number that breaks the pattern. That's why only a proof will do. And let's be honest, part of the appeal is how deceptively playful it is. You can hand this problem to a 10-year-old, and they'll understand it instantly. Then you can hand it to a Fields medalist, one of the top mathematicians in the world, and they'll scratch their head just as helplessly. It's one of those rare puzzles that humbles everyone equally. It's even been given nicknames, the hailstone sequence, because numbers go up and down like hailstones bouncing in a storm. The hailstone problem, or sometimes just the simplest impossible math problem, which honestly sounds like a great tagline for a movie. Coming this summer, The Simplest Impossible Math Problem, starring Matt Damon as a troubled genius who can't stop dividing by 2. And the best part? You don't need a chalkboard or a computer to play. You can do it in your head, on a napkin, on the back of a grocery list, which means mathematicians never escape it. They'll be at dinner, someone says a number, and suddenly they're lost, calculating whether 73 eventually falls into the 4-2-1 loop. Spoiler, it does. That's the Collatz Conjecture, a tiny, simple bedtime riddle that refuses to be solved. It's not flashy like the Riemann Hypothesis. It's not high-tech like P versus NP. It's just a humble little game that hides infinite mystery behind its childlike rules. And in the next chapter, we'll dig deeper into why it's so simple, yet so impossible. Because sometimes, the easiest-looking puzzles are the ones that end up breaking our brains the most. On the surface, the Collatz Conjecture looks like the kind of math puzzle you'd find in a children's activity book right next to connect the dots and colour by numbers. The rules fit in one sentence. If it's even, divide by 2. If it's odd, triple it and add 1. Easy. So why have some of the smartest mathematicians in history spent nearly a century banging their heads against it? The answer is that the Collatz Conjecture is the mathematical equivalent of a wolf in sheep's clothing. It looks cute, it looks harmless, but the second you try to prove it, it bites. Let's break it down. When you start playing with small numbers, the pattern feels obvious. 6 collapses down quickly. 10 takes a little detour, but still gets to 1. 27 goes on a wild road trip, stopping at 9,232 before finally coming home. But no matter what number you try, it always lands in the 4-2-1 loop. Every time. It feels inevitable. And that's the problem. Feeling inevitable and proving inevitable are two very different things. Mathematicians have thrown every tool they can at Collatz. Probability theory, chaos theory, number theory. None of it has cracked the nut. Computers have checked trillions of starting numbers. Every single one falls into the loop, but computers don't do infinity. Infinity just yawns and says, "Nice try, mortal." So the big question remains, is there some number out there that refuses to play along? Some massive stubborn rebel that never drops into the loop? If such a number exists, it's hiding very, very well. Paul Erdos, remember him, the prolific mathematician who basically treated math like an extreme sport, looked at Collatz and declared it hopeless. He meant it in the most affectionate way possible. He loved hopeless problems. To him, hopeless meant beautiful. But still, when someone with 1,500 papers under his belt throws up his hands and says, "Nope," you know you're in trouble. So why is it so impossible? Well, one reason is that the Collatz process mixes two totally different behaviors. The divide by 2 step makes numbers shrink. The triple it and add 1 step makes numbers explode upward. Put those two together, and you get a chaotic dance that's impossible to predict. One step pulls you down, the next launches you up. It's like trying to predict the path of a drunk kangaroo on a trampoline. Sometimes you land in a quick fall straight to 1. Other times you bounce all over the place before settling down. The unpredictability is the heart of the mystery. Here's a fun thought. Imagine someone says, "I can prove Collatz is true." How would they even start? You'd have to show that every possible number eventually falls to 1. Not just a million numbers, not just a trillion. Every single number, all the way to infinity. And infinity, my friends, is annoyingly infinite. What if instead someone says, "I can disprove it"? That would mean finding one single number that doesn't fall into the loop. Just one. But so far, no one has found it. Which means Collatz is stuck in this twilight zone. True for everything we can see, unproven in the world we can't. That's why some people compare it to an unsolvable riddle. It's not just a math puzzle. It's a reflection of how little we actually understand about numbers. Something as basic as divide by 2 or triple and add 1 can unleash chaos that refuses to be tamed. And maybe that's why the problem is so captivating, because it's simple enough that anyone can play with it, but deep enough that nobody can solve it. It's math's version of a trapdoor spider. Looks harmless, then suddenly, wham, you're stuck. Mathematicians even give names to problems like this, deceptively simple or toy problems. The idea is that they look like toys, like games, but hidden inside is a labyrinth. And the Collatz Conjecture is one of the most notorious toys of all. Let me put it another way. Imagine you're hiking and you find a little cave. Looks small, looks harmless. You step inside thinking it'll be a fun 5-minute detour. Then you realise the cave tunnels stretch for miles underground, twisting and turning, no end in sight. That's what happens when you play with Collatz. And it's not just a math curiosity, it's taught mathematicians humility. It reminds us that even the simplest seeming systems can produce mind-boggling complexity, that the line between order and chaos is thinner than we think. The beauty is in the contradiction. It's simple, but impossible, childlike but maddening, predictable but chaotic. The Collatz Conjecture lives in that strange space, laughing at anyone who dares to tame it. So next time you're bored, try it. Pick a number, run it through the rules, watch it climb and fall, zigzagging around until it drops into the 4-to-1 loop. It's strangely soothing, like watching a squirrel try to navigate a bird feeder. And as you do it, remember you're playing the same game that has confounded the best mathematicians alive. And here's the kicker. If someone ever proves Collatz one way or the other, it'll be monumental. If it's true, we'll have finally wrangled chaos into submission. If it's false, we'll have discovered a number that lives outside the loop, lurking in the wilderness of infinity. Either way, It'll be historic. But until then, the Collatz conjecture remains what it has always been, the simplest impossible problem, a bedtime riddle that refuses to go to sleep. And speaking of chaos, in the next chapter we'll look at how Collatz connects to something even bigger, the world of chaos theory. Because believe it or not, this little odd, even game might hold clues to how complexity itself arises in the universe. At first glance, the Collatz conjecture looks like child's play. Divide by 2 if even, triple and add 1 if odd, rinse and repeat. It feels like the kind of puzzle you doodle on the back of a grocery list while waiting for your pasta water to boil. But here's the twist. Hidden inside this simple rule is chaos. Real, terrifying, universe-grade chaos. Let's talk about chaos theory for a second. Chaos theory isn't about things being messy, though your bedroom floor might qualify as a research project. It's about systems that look random but are actually ruled by very simple rules. Weather is a classic example. The rules of weather are basic physics: temperature, air pressure, humidity. But put them together and suddenly you've got hurricanes and thunderstorms, and the fact that it always rains the day you forget an umbrella. The Collatz conjecture is like a tiny chaos machine disguised as arithmetic homework. The rules are laughably simple, but the sequences they generate look completely unpredictable. Start with one number, and you might fall to 1 in just a few steps. Start with another, and you might rocket into the thousands before finally crashing down. The path is impossible to predict by intuition alone. That's why mathematicians sometimes call the Collatz problem the hailstone sequence. Imagine a hailstone bouncing around in the sky. It shoots upward in strong winds, then falls, then rises again, zigzagging until finally hitting the ground. That's exactly what Collatz numbers do: up, down, until they finally settle into the 4-1 loop. Now, why does this matter? Because it's a perfect example of how chaos hides in plain sight. You don't need fancy physics to find unpredictability. You don't need quantum mechanics or black holes. You just need the number 3, a plus sign, and a division by 2. Bam! Chaos. This connection has fascinated researchers for decades. Collatz isn't just a cute puzzle. It's a microcosm of how simple rules can create unpredictable, complex behavior. That's the same principle behind fractals, turbulence, population growth, and about half the arguments you've ever had with your printer. Here's another twist. Some researchers think studying Collatz might actually shed light on other chaotic systems. The unpredictability of the sequence feels random, but it's not true randomness, it's deterministic. That means if you start with the same number, you always get the same sequence. There's no dice roll, no coin flip. It's fixed, and yet it looks random, just like weather patterns or stock markets. This is the part where you start to realize Collatz isn't just about numbers, it's about the universe. It's about how order and disorder coexist, how simple laws can give rise to patterns that feel unpredictable but are in fact perfectly determined. That's chaos theory in a nutshell. And here's where we bring back our old friend Paul Erdos. When he called the Collatz conjecture utterly hopeless, he wasn't just being grumpy. He meant that the problem straddles this weird border between structure and chaos. It looks like there should be a neat proof hiding somewhere, but every time you try to grab it, it dissolves into unpredictability, like trying to catch smoke with your bare hands. Even the way mathematicians talk about Collatz sounds like chaos theory poetry. They describe the trajectory of a number. They talk about orbiting sequences. It's as if each number is a little planet spinning in its own strange path, before finally spiraling into the black hole of the 4-1 loop. And of course, this leads to jokes. Mathematicians have a dark sense of humour. There's a running gag that if aliens ever show up and say, "Solve this or we destroy your planet," and they hand us the Collatz conjecture, then, well, nice knowing you. Goodbye Earth, because no one's solving it anytime soon. But jokes aside, Collatz really is a reminder of how easily chaos hides inside the ordinary. Think about it. Numbers, the most basic building blocks of logic and order, are secretly hosting one of the wildest chaotic dances we've ever seen. It's like discovering that the tidy librarian has a secret life as a heavy metal drummer. What makes it especially haunting is that the chaos is still caged. Every number we've ever checked eventually falls into the loop, so it's chaos with a leash. It bounces around unpredictably, but always comes home, unless of course there's a number out there in infinity that doesn't, and that possibility is what keeps mathematicians awake at night. Because here's the scary part. If even one number escapes, just one, it would mean the Collatz Conjecture is false, and the entire story we've been telling ourselves about this chaotic little game would crumble. Infinity doesn't care how many numbers we've checked. Infinity just sits there smirking, holding all its secrets. So when mathematicians stare at Collatz, they're not just staring at a puzzle, they're staring into the nature of complexity itself. They're asking, how can such a tiny rule generate so much unpredictability? And if unpredictability is baked into something as simple as odd and even, what does that say about the rest of the universe? That's why Collatz has earned such a legendary status. Not because it's flashy, not because it's tied to $1 million prize, but because it feels like chaos in disguise. A bedtime riddle that turns into a meditation on the limits of knowledge. And if you're listening to this as you drift off to sleep, think of it this way. Every number is like a traveller, wandering through the strange landscape of the Collatz world. Some take short trips, some wander for ages, but in the end they all come home to the little village of 4, 2 and 1. At least that's what we think. Next, we'll look at how mathematicians themselves have reacted to this riddle. The obsession, the frustration, the funny little anecdotes about people who got lost in Collatz land and never came back. Because while the problem may be hopeless, the stories it generates are endlessly entertaining. By now you've probably noticed a pattern. Mathematics is full of puzzles that look harmless, but when you actually try to solve them, they transform into brain-eating monsters. The Riemann Hypothesis, P versus MP, the Collatz Conjecture, they all share that magical ability to lure you in with a smile and then leave you crying into your notebook. So in the year 2000, the Clay Mathematics Institute decided to make things official. They announced what they called the Millennium Prize problems. 7 of the hardest unsolved problems in all of mathematics. Each one comes with a prize of $1 million. 7 problems, $7 million, and let's be honest, 7 ways to ruin your social life trying to solve them. It was like math's version of the Hunger Games. Except instead of teenagers with bows and arrows, you've got professors with chalk and too much coffee. So what are these 7 legendary monsters? Let's take a little tour. First, of course, is our old friend, the Riemann Hypothesis. We've already met this one. The shy German, the mysterious zeros, the fate of the internet. It's the crown jewel of the Millennium List, the one everyone knows, the Beyoncé of unsolved math problems. Then there's P versus NP. We've also met this troublemaker, the hacker's dream, the computer scientist's nightmare. If solved, it could either save the world or destroy it. No middle ground. Definitely deserving of $1 million bounty. Next up is the Poincaré Conjecture. This one's about the shape of the universe. It asks roughly, if you've got a 3-dimensional space with no holes, is it basically just a fancy version of a sphere? Henri Poincaré posed this question back in 1904, and it haunted mathematicians for a century. But here's the twist. This one was actually solved. Grigory Perelman, a Russian mathematician with a taste for isolation, cracked it in 2003. He won the $1 million prize and then turned it down. More on that story in the next chapter, because trust me, it's wild. Then we have the Yang-Mills existence and mass gap problem. This one lives in the world of physics. It has to do with quantum field theory, the stuff that describes particles and forces at the smallest scales. The problem is physicists are pretty sure Yang-Mills theory works, but nobody can actually prove it in a rigorous mathematical way. It's like having a car that drives perfectly but not being able to prove that the engine exists. Next is the Navier-Stokes existence and smoothness problem. This one is about fluids. The Navier-Stokes equations are what we use to describe how air moves, how water flows, how coffee sloshes around in your mug. They work beautifully in practice, but mathematicians don't know if solutions to these equations always behave nicely, or if sometimes they go completely berserk. Which means we don't actually know if the math behind weather, turbulence and airplane design is fully sound. Comforting, right? Then there's the Birch and Swinnerton-Dyer conjecture. This one lives in the land of number theory, and it's a beast. It has to do with elliptic curves, curves that look like elegant loops and swirls, and whether you can figure out how many rational points live on them. It sounds niche, but it connects to deep questions about numbers, cryptography, and algebraic geometry. Think of it as the obscure indie film of the Millennium Problems. Not many people understand it, but the ones who do are obsessed. Finally, there's the Hodge Conjecture. This one is about shapes and geometry in higher dimensions. It asks whether certain kinds of shapes, algebraic cycles, exist to explain the complicated structures of spaces. If that sentence made your eyes glaze over, don't worry, you're not alone. Even mathematicians groan at this one. The Hodge conjecture is like the artsy abstract painting of the group. You stare at it, nod slowly, and pretend you understand. So there you have it, the 7 millennium problems, Riemann Hypothesis, P versus NP, Poincare conjecture, already solved, Yang-Mills and the mass gap, Navier-Stokes existence and smoothness, Birch and Swinnerton-Dyer conjecture, Hodge conjecture. Solve any one of these and you get $1 million. Solve all 7 and you're $7 million richer. Though realistically, if you solved all 7, money would be the least of your prizes. You'd basically be the math version of a rock god. But here's the funny thing. Mathematicians don't really chase these problems for the money. $1 million is nice, sure, but many of them are already comfortably employed as professors. What really matters is the glory, the bragging rights, the immortality of having your name attached to one of the great triumphs of human thought. The Clay Institute knew this. They weren't just dangling cash. They were dangling the chance to write your name in history, alongside Newton, Euler, Gauss and Riemann. And that's a prize no amount of money can buy. Of course, the irony is that the Millennium List was announced in 2000, and over 2 decades later, only one of the 7 has been solved. 6 still stand, staring down humanity, daring anyone to make a move. And every time someone claims to have cracked one, the math community gathers, pokes it with sticks, and usually pronounces it dead within days. Still, the list serves an important role. It focuses attention. It gives young mathematicians mountains to climb. It reminds the world that math isn't finished, that there are still mysteries out there, hiding just beyond reach. And sometimes those mysteries come with stories that are stranger than fiction. Which brings us to the tale of the one problem that was solved, the man who solved it, and why he walked away from $1 million and from mathematics itself. Most people, if handed a check for $1 million, would not hesitate. You'd grab it, maybe do a little victory dance, and start mentally building your dream house with the indoor slide and the infinity pool. But in the world of mathematics, nothing is ever that simple. Enter Grigori Perelman, the man who solved one of the greatest problems of all time, and then calmly said no thanks to both the prize money and the spotlight. The story begins with the Poincare conjecture, one of those brain-melting geometry problems that sounds simple until you actually try to understand it. In short, it asks, if you've got a 3-dimensional space with no holes, is it basically just a fancy sphere? Henri Poincare posed the question in 1904, and for 100 years it mocked mathematicians from the shadows, refusing to budge. Then, in 2003, Perelman posted a series of papers online, not in a fancy journal, not with any fanfare, just casually dropped them on the internet like someone uploading vacation photos. In these papers, he outlined a brilliant, mind-bending solution to the Poincare conjecture, using something called Ricci flow, which is basically the mathematical equivalent of smoothing out wrinkles in a crumpled shirt. Slowly, other mathematicians checked his work, and checked, and rechecked. After years of scrutiny, they realized Perelman had done it. He'd solved the century-old riddle. So in 2010, the Clay Mathematics Institute awarded him the $1 million Millennium Prize. They invited him to ceremonies, offered him glory, interviews, the mathematical equivalent of a ticker-tape parade. And Perelman? He just shrugged and said, no thanks. Let me repeat that. The man solved a problem that haunted mathematics for a century, won $1 million and walked away. He didn't want the money. He didn't want the fame. He didn't even want to hang out with other mathematicians at conferences. He just disappeared back into his quiet life in St. Petersburg, living with his mother in a modest apartment, occasionally spotted buying groceries or feeding stray cats. Why? That's the $1 million question. Literally. Perelman later explained that he didn't care about prizes or recognition. For him, solving the problem was enough. He felt that the mathematical community was corrupt, too obsessed with fame and credit. At one point there was even controversy where other mathematicians tried to grab a slice of the glory for his proof, and Perelman wanted no part of that circus. He told a reporter, "I don't want to be on display like an animal in a zoo," which, honestly, is kind of fair. Imagine being dragged into endless interviews, ceremonies, banquets, all because you solved something for the pure joy of it. If you're an introvert who loves math, that sounds like a nightmare. What's even more interesting is that Paromon didn't just refuse the Clay Prize. A few years earlier, he'd also turned down the Fields Medal, often called the Nobel Prize of Mathematics. Twice he said no to global recognition. Twice he stepped out of the spotlight. And that's when the legend of Grigori Perelman really began. He became a sort of mythic figure, the hermit genius who cared only about truth, not about wealth or glory. In a world where most people would trip over themselves for even 5 minutes of fame, Perelman's rejection made him larger than life. Some people even started comparing him to characters out of novels, the reluctant hero, the monk-like sage who walks away from worldly temptations. Others, less romantically, said he was just eccentric. But whatever you call it, his decision shocked the world. And here's the thing, Perelman's refusal isn't just about one man. It tells us something bigger about mathematics itself. At its core, math isn't about prizes or money. It's about curiosity, about the joy of solving something difficult, about uncovering a piece of truth that was hidden all along. Perelman lived that principle to the extreme. For him, the beauty of the solution was the only reward he wanted. Of course, that doesn't mean people stopped obsessing over him. Journalists camped outside his apartment, documentaries were made, mathematicians whispered stories about spotting him in parks. Still deep in thought, he became a mystery in his own right, another unsolved problem, this time not about numbers but about human nature. And honestly, isn't that kind of perfect? The man who solved a century-old riddle then turned himself into a riddle, a walking paradox, a genius who wanted nothing, a hero who refused the crown, a millionaire who chose to stay broke. If math had its own comic book universe, Perelman would be the enigmatic anti-hero, the one who saves the world, then vanishes into the shadows, leaving everyone to wonder if he'll ever return. So the next time someone says, "Wouldn't you love to win $1 million?" think of Grigori Perelman. Think of the man who said no, and in doing so became immortal in a way no prize could ever grant. And speaking of immortality, the Millennium Problems aren't just about prizes or fame, they're about the endless mysteries that drive mathematicians to the brink of obsession. In the next chapter, we'll peek at some of the other unsolved problems, ones that didn't even make the Clay list, but which continue to haunt, inspire, and sometimes ruin the lives of those who chase them. Most people, if handed a check for $1 million, would not hesitate. You'd grab it, maybe do a little victory dance, and start mentally building your dream house with the indoor slide and the infinity pool. But in the world of mathematics, nothing is ever that simple. Enter Grigori Perelman, the man who solved one of the greatest problems of all time, and then calmly said no thanks to both the prize money and the spotlight. The story begins with the Poincare conjecture, one of those brain-melting geometry problems that sounds simple until you actually try to understand it. In short, it asks, if you've got a three-dimensional space with no holes, is it basically just a fancy sphere? Henri Poincare posed the question in 1904, and for 100 years it mocked mathematicians from the shadows, refusing to budge. Then, in 2003, Perelman posted a series of papers online. Not in a fancy journal, not with any fanfare, just casually dropped them on the internet like someone uploading vacation photos. In these papers, he outlined a brilliant, mind-bending solution to the Poincare conjecture using something called Ricci flow, which is basically the mathematical equivalent of smoothing out wrinkles in a crumpled shirt. Slowly, other mathematicians checked his work, and checked, and rechecked. After years of scrutiny, they realized Perelman had done it. He'd solved the century-old riddle. So in 2010, the Clay Mathematics Institute awarded him the $1 million Millennium Prize. They invited him to ceremonies, offered him glory, interviews, the mathematical equivalent of a ticker-tape parade. And Perelman, he just shrugged and said, no thanks. Let me repeat that. The man solved a problem that haunted mathematics for a century, won $1 million, and walked away. He didn't want the money. He didn't want the fame. He didn't even want to hang out with other mathematicians at conferences. He just disappeared back into his quiet life in St. Petersburg, living with his mother in a modest apartment, occasionally spotted buying groceries or feeding stray cats. Why? That's the $1 million question. Literally. Perelman later explained that he didn't care about prizes or recognition. For him, solving the problem was enough. He felt that the mathematical community was corrupt, too obsessed with fame and credit. At one point there was even controversy where other mathematicians tried to grab a slice of the glory for his proof, and Perelman wanted no part of that circus. He told a reporter, "I don't want to be on display like an animal in a zoo," which honestly is kind of fair. Imagine being dragged into endless interviews, ceremonies, banquets, all because you solved something for the pure joy of it. If you're an introvert who loves math, that sounds like a nightmare. What's even more interesting is that Perelman didn't just refuse the Clay Prize. A few years earlier, he'd also turned down the Fields Medal, often called the Nobel Prize of Mathematics. Twice he said no to global recognition. Twice he stepped out of the spotlight. And that's when the legend of Grigori Perelman really began. He became a sort of mythic figure, the hermit genius who cared only about truth, not about wealth or glory. In a world where most people would trip over themselves for even 5 minutes of fame, Perelman's rejection made him larger than life. Some people even started comparing him to characters out of novels, the reluctant hero, the monk-like sage who walks away from worldly temptations. Others, less romantically, said he was just eccentric. But whatever you call it, his decision shocked the world. And here's the thing, Perelman's refusal isn't just about one man. It tells us something bigger about mathematics itself. At its core, math isn't about prizes or money. It's about curiosity, about the joy of solving something difficult, about uncovering a piece of truth that was hidden all along. Perelman lived that principle to the extreme. For him, the beauty of the solution was the only reward he wanted. Of course, that doesn't mean people stopped obsessing over him. Journalists camped outside his apartment, documentaries were made, mathematicians whispered stories about spotting him in parks. Still deep in thought, he became a mystery in his own right, another unsolved problem, this time not about numbers but about human nature. And honestly, isn't that kind of perfect? The man who solved a century-old riddle then turned himself into a riddle, a walking paradox, a genius who wanted nothing, a hero who refused the crown, a millionaire who chose to stay broke. If math had its own comic book universe, Perelman would be the enigmatic anti-hero, the one who saves the world, then vanishes into the shadows, leaving everyone to wonder if he'll ever return. So the next time someone says, "Wouldn't you love to win $1 million?" think of Grigori Perelman. Think of the man who said no, and in doing so became immortal in a way no prize could ever grant. And speaking of immortality, the Millennium Problems aren't just about prizes or fame. They're about the endless mysteries that drive mathematicians to the brink of obsession. In the next chapter, we'll peek at some of the other unsolved problems, ones that didn't even make the Clay list, but which continue to haunt, inspire, and sometimes ruin the lives of those who chase them. Mathematics has a reputation for being logical, clean, precise, the ultimate science of order. But here's the secret nobody tells you. Math also drives people insane, not in the I can't balance my checkbook sense, but in the deep, all-consuming obsession sense. Some of the greatest mathematicians in history have been swallowed whole by problems that refuse to let go. Take Kurt Gödel, for instance. He was one of the most brilliant logicians of all time, famous for his incompleteness theorems, which basically said, no matter how many rules you make, there will always be true statements you can't prove. It was a mathematical earthquake. But Gödel himself spiraled into paranoia. He became convinced that people were trying to poison him, and in the end he refused to eat food unless his wife tasted it first. When she was hospitalized, he stopped eating altogether and tragically starved. That's not just math, it's math madness. Or think of Paul Erdos, the eccentric genius who lived out of a suitcase, fueled by coffee and amphetamines, traveling the world to collaborate with anyone who would have him. He didn't care about money, didn't care about possessions. What he cared about was problems. He described a book in which God kept the most beautiful proofs, and he spent his life trying to glimpse its pages. People close to him joked that he wasn't addicted to drugs. He was addicted to math, and the drugs were just there to keep him awake long enough to keep working. Then there's Alexander Grothendieck, one of the greatest mathematicians of the 20th century. He revolutionized algebraic geometry, made it practically a new language, but later in life he became increasingly disillusioned with the academic world. He abandoned his career, withdrew from society, and spent his last decades living in seclusion in the French Pyrenees, surrounded by forests, writing thousands of pages of manuscripts that may or may not ever be fully understood. Even more haunting is the story of Srinivasa Ramanujan, the self-taught genius from India. He had almost no formal training, but he filled notebooks with results so bizarre and original that professional mathematicians could hardly believe their eyes. He said the goddess Namagiri whispered formulas to him in dreams. Tragically, he died at just 32, leaving behind a treasure trove of insights that mathematicians are still unpacking today. Imagine how many riddles he might have solved if he'd lived longer. What ties all these stories together is obsession. Mathematics is full of problems that look so simple, so innocent, that they trick people into giving them just a few hours. Then those hours become days, the days become decades, and before you know it, your whole life has been swallowed by one unsolved riddle. The Collatz Conjecture is a perfect example. Entire careers have been sunk into this tiny little odd-even game. People joke that it's like quicksand. You step in just to test the water, and suddenly you're up to your neck. Erdos himself warned younger mathematicians to stay away from it unless they wanted to waste their time. And yet people still dive in, convinced they'll be the one to crack it. There's a fine line here. Obsession can be dangerous, yes, but it's also the engine of discovery. If nobody ever got obsessed, we'd never have the breakthroughs that changed the world. You don't prove Fermat's last theorem by glancing at it casually on a Sunday afternoon. Andrew Wiles, the man who did finally solve it, spent 7 years secretly working in his attic office, chasing one idea until it finally clicked. That's not casual, that's obsession. And mathematicians know this about themselves, they joke about it. You'll hear stories of professors scribbling equations on napkins at dinner, or filling bathroom mirrors with formulas in dry erase markers. There are urban legends about marriages destroyed by equations, children named after theorems, and mathematicians who literally dreamed solutions in their sleep. But behind the humour, there's something deeper. These problems exert a strange gravitational pull. They don't just live on chalkboards, they live in people's heads. They whisper, they nag, they become companions, enemies, lifelong shadows. That's why some mathematicians compare their work to art, or even to love. It's not a job, it's not even a passion, it's a compulsion. When a problem grabs hold of you, it doesn't let go. You don't solve it because you want to. You solve it because you can't stop thinking about it. Of course, sometimes the obsession ends badly. There are tragedies, burnouts, broken lives, but sometimes obsession leads to beauty, to proofs so elegant they make people cry, to discoveries that reshape human knowledge. And maybe that's why we're so fascinated by these unsolved mysteries. They're not just problems on a page. They're stories about human beings, about our limits, our madness, and our brilliance. Every conjecture, every hypothesis, every stubborn equation is also a mirror reflecting the people who wrestle with it. So when we talk about math driving people mad, it's not just about chalk dust and sleepless nights. It's about the human cost of curiosity, the price of chasing infinity. But it's not all tragedy. In the next chapter, we'll look at the brighter side of not knowing, because for all the obsession, frustration, and heartbreak, there's also joy. There's beauty in mystery itself. And maybe, just maybe, the fact that some problems remain unsolved is what makes mathematics so endlessly alive. When you think of mathematics, you probably imagine certainty. 2 + 2 = 4. Triangles have 3 sides. The sun will rise, and your calculator will never argue with you. Math feels like the one place where everything is solid and absolute. But here's the wonderful paradox. Some of the greatest beauty in mathematics comes not from the answers, but from the questions we can't answer, from the mysteries that sit there unsolved, daring us to dream about them. Think about it. If every problem had a neat solution, mathematics would be like a crossword puzzle book you finish in one sitting. Fun for a while, but then what? The joy of math isn't that it's done, it's that it's endless. Every time we solve one riddle, 10 more pop up, like Hydra heads in Greek mythology. The unknown isn't a flaw, it's the feature that keeps the whole adventure alive. Take the Riemann Hypothesis. It's been sitting there since the 19th century, mocking mathematicians, refusing to give up its secret. But in that refusal, it's inspired entire fields of research, countless new techniques, and whole careers of brilliant people who might otherwise never have existed. If Riemann had neatly proved it in his lifetime, we would have lost a century and a half of mathematical exploration. Or the Collatz Conjecture, that silly little game of odd and even. If someone proves it tomorrow, it'll be a wonderful day. But part of me thinks the world would lose something too. Right now, Collatz is a playground. Anyone can try it. Children can experiment with it. Professionals can chase it. It's a reminder that math is still full of surprises hiding in plain sight. If it gets solved, it becomes another entry in the textbook. Important, yes, but no longer mysterious. And mystery is what makes our eyes sparkle. The beauty of not knowing is that it keeps math human. It keeps us humble. We like to think we're masters of logic, rulers of the universe, clever enough to put people on the moon and build smartphones that recognize our faces. But then a simple puzzle about numbers comes along and says, "Cute, try harder." And we're reminded that the universe still has secrets bigger than us. It's also what makes math communal. When a problem is unsolved, it belongs to everyone. The Riemann Hypothesis doesn't belong to one mathematician. It belongs to the whole community, passed like a torch from generation to generation. Students try it, professors try it, hobbyists try it. It becomes a shared story, a shared frustration, even a shared joke. Still unsolved? Yep, still unsolved. And sometimes the joy is in the journey itself. Mathematicians often say that chasing a problem teaches you more than solving it. You might not crack the big riddle, but along the way you discover beautiful side paths, clever techniques, unexpected connections. Andrew Wiles worked for years on Fermat's last theorem, and when he finally proved it, the real prize wasn't just the solution. It was all the new mathematics that bloomed along the way. There's also something strangely comforting about the unsolved. If math had already answered every question, it would feel like a closed book, cold, finished. Instead, it feels alive, like an open landscape with mountains still unclimbed. There's always another horizon, another mystery calling. That's why mathematicians talk about their subject the way poets talk about love. It's not just numbers, it's adventure. And maybe this is the part that makes it perfect for bedtime. Because mystery is soothing, it reminds us that we don't have to have all the answers tonight. We can let questions rest. We can drift off knowing that some problems are bigger than us. And that's okay. The universe will keep spinning. The numbers will keep whispering. And we'll keep chasing them tomorrow. So yes, mathematics has its maddening side. It can break hearts, ruin sleep schedules, and turn brilliant minds into obsessed hermits. But it also has this gentle, beautiful side. The side that says, it's okay not to know. It's okay to wonder. It's okay to sit with mystery. Because in the end, maybe the goal isn't to solve everything. Maybe the goal is just to keep asking, to keep exploring, to keep laughing at how a simple odd and even game can outsmart us all. And that, my friends, is the beauty of not knowing. In the next and final chapter, we'll wrap everything together. We'll reflect on why these impossible problems matter, not just to mathematicians, but to all of us, and why maybe, just maybe, the fact that some riddles remain unsolved is the greatest gift mathematics gives us. When you think of mathematics, you probably imagine certainty. 2 + 2 = 4. Triangles have 3 sides. The sun will rise and your calculator will never argue with you. Math feels like the one place where everything is solid and absolute. But here's the wonderful paradox. Some of the greatest beauty in mathematics comes not from the answers, but from the questions we can't answer. From the mysteries that sit there unsolved, daring us to dream about them. Think about it. If every problem had a neat solution, mathematics would be like a crossword puzzle book you finish in one sitting. Fun for a while, but then what? The joy of math isn't that it's done, it's that it's endless. Every time we solve one riddle, 10 more pop up, like Hydra heads in Greek mythology. The unknown isn't a flaw, it's the feature that keeps the whole adventure alive. Take the Riemann Hypothesis. It's been sitting there since the 19th century, mocking mathematicians, refusing to give up its secret. But in that refusal, it's inspired entire fields of research, countless new techniques, and whole careers of brilliant people who might otherwise never have existed. If Riemann had neatly proved it in his lifetime, we would have lost a century and a half of mathematical exploration. Or the Collatz Conjecture, that silly little game of odd and even. If someone proves it tomorrow, it'll be a wonderful day. But part of me thinks the world would lose something too. Right now, Collatz is a playground. Anyone can try it. Children can experiment with it. Professionals can chase it. It's a reminder that math is still full of surprises hiding in plain sight. If it gets solved, it becomes another entry in the textbook. Important, yes, but no longer mysterious. And mystery is what makes our eyes sparkle. The beauty of not knowing is that it keeps math human. It keeps us humble. We like to think we're masters of logic, rulers of the universe, clever enough to put people on the moon and build smartphones that recognize our faces, but then a simple puzzle about numbers comes along and says, "Cute, try harder," and we're reminded that the universe still has secrets bigger than us. It's also what makes math communal. When a problem is unsolved, it belongs to everyone. The Riemann hypothesis doesn't belong to one mathematician, it belongs to the whole community, passed like a torch from generation to generation. Students try it, professors try it, hobbyists try it. It becomes a shared story, a shared frustration, even a shared joke. Still unsolved? Yep, still unsolved. And sometimes the joy is in the journey itself. Mathematicians often say that chasing a problem teaches you more than solving it. You might not crack the big riddle, but along the way you discover beautiful side paths, clever techniques, unexpected connections. Andrew Wiles worked for years on Fermat's last theorem, and when he finally proved it, the real prize wasn't just the solution. It was all the new mathematics that bloomed along the way. There's also something strangely comforting about the unsolved. If math had already answered every question, it would feel like a closed book, cold, finished. Instead, it feels alive, like an open landscape with mountains still unclimbed. There's always another horizon, another mystery calling. That's why mathematicians talk about their subject the way poets talk about love. It's not just numbers, it's adventure. And maybe this is the part that makes it perfect for bedtime. Because mystery is soothing. It reminds us that we don't have to have all the answers tonight. We can let questions rest. We can drift off knowing that some problems are bigger than us. And that's okay. The universe will keep spinning, the numbers will keep whispering, and we'll keep chasing them tomorrow. So yes, mathematics has its maddening side. It can break hearts, ruin sleep schedules, and turn brilliant minds into obsessed hermits. But it also has this gentle, beautiful side. The side that says, it's okay not to know. It's okay to wonder. It's okay to sit with mystery. Because in the end, maybe the goal isn't to solve everything. Maybe the goal is just to keep asking, to keep exploring, to keep laughing at how a simple, odd and even game can outsmart us all. And that, my friends, is the beauty of not knowing. In the next and final chapter, we'll wrap everything together. We'll reflect on why these impossible problems matter, not just to mathematicians but to all of us, and why maybe, just maybe, the fact that some riddles remain unsolved is the greatest gift mathematics gives us.